Okay, welcome to the next lecture in KDD. Today we will be finishing up the chapter of preprocessing and we will get into the chapter of online analytical processing and data warehousing after that. If I'm correct, we stopped last week at the slide for the subchapter of data transformation and data discretization. So we are at the last subchapter of preprocessing. Are there any questions regarding the previous subchapters of preprocessing? Doesn't look like it. Okay, then we will finish up the chapter of preprocessing with some normalization and some data discretization. Data transformations in general are functions that are applied to a set of samples or set of data points, which are most often samples, to transform the data into another data set. Into, for example, a smooth data set to remove noise from the data. We can generate new attributes and features. We talked about that last week as well. PCA was creating new features out of our features. We can, of course, summarize data that will become pretty relevant in data warehousing, so in the next chapter. And we can do things like normalization and discretization, which are the focus of this subchapter. We already talked about normalization a little bit in the previous chapter of data, where we talked about standardization, which is also called Z-score normalization. So standardization and Z-score normalization are pretty much the same, just another word for that. Today we will also talk about min-max normalization and normalization by decimal scaling, which have different focuses. And we will also talk about discretization. Let's start with normalization. Since we already talked about standardization or Z-score normalization, we can pretty much skip over that. You already know this formula. In Z-score normalization or standardization, you will take the value, subtract the mean of the attribute, and divide it through the standard deviation of the attribute. So in a little example, you will be able to compute that. However, I will skip around that. The big advantage of Z-score normalization is that we get to a standard deviation of 1 for the result. So the resulting attribute has a standard deviation of 1 guaranteed, which is pretty nice for some methods. For example, for PCA. That's why we are using standardization in PCA. However, we also want some other normalization techniques. One of the simpler ones is the min-max normalization, where we try to not alter the standard deviation of a result, but we try to put the result into a certain minimum and maximum interval. So for example, we can say we want min-max normalization for an interval of 0 to 1, then all of the resulting values will be put into the interval of 0 to 1. So we know that the lowest value ends up at 0, the highest value ends up at 1. If we, for example, try to min-max normalize an income range, and we know that the lowest value of that income range is $12,000 and the highest value is $98,000. And we try to normalize it to 0 to 1. Then of course, the lowest value, so $12,000, ends up at 0. The highest value ends up at 1. And any middle value can be mapped using this formula. So if we are, for example, taking a look at $73,600, we put that into this formula, put $73,600 minus the minimum, so $12,000, divided through the difference between the maximum and the minimum, multiply it with the interval range we want to apply, so 0 to 1, and add the minimum. And we end up at 0.716. Which is also nice, since the 0.716 is pretty much the position in the interval range, percentage-wise, where the value ends up. So the value is at 71.6% of the value range. Min-max normalization has a big advantage that it totally 100% uses the whole interval range. So we are not losing any space in the interval range. This will become relevant once we get to the next normalization techniques, normalization by decimal scaling, since that isn't using the whole interval range. Big advantage of min-max normalization compared to z-score normalization is that we know what the value range is. We know that we will not have any value above 1 for min-max normalization from 0 to 1. While in z-score normalization, we can't really say which is the maximum value. We only know that the standard deviation of the attribute will be 1. But the highest value might as well be 3, whatever. That might happen. As you see, it's not that easy to compute if we don't know if the lowest value and highest value doesn't end up at exactly 0 or 100 or things like that. So it's not that easy to comprehend. We also have normalization by decimal scaling, which is a technique which is far easier to comprehend the values of. Normalization by decimal scaling is just a technique where you try to also put values into a certain interval range, most often -1 to 1. Well, not most often, -1 to 1, that's given. And you try to find any k which puts all the values into this interval range. So for example, if we have something like these values, 1, 10, 19. If we want to divide that through any 10 to the power of k, to put all the values into the interval range of -1 to 1, then we have to select, we have to select k equals 2. So 10 to the power of 2. So 1 ends up as 1 divided through 10 to the power of 2. So 1 divided through 100 is 0.01. For 10, it's 0.1, and for 19, it's 0.19. This puts everything in the interval of -1 to 1. However, it doesn't use value range completely. So we know that everything from -1 to 0 isn't to 0.01 isn't even used, because the lowest value ends up at 0.01. And with 0.19, we also do not use everything up to 1. However, normalization by decimal scaling is far easier to comprehend because you can easily see that the 19 seems to be the 0.19. You easily can see that the 10 ends up at 0.1. So it's far easier to comprehend as a human mind. While it's hard to see that in min-max normalization, 73,000 ends up at 0.71. In this case, it's pretty easy to comprehend. And basically, that's the difference between min-max normalization and normalization by decimal scaling. You use normalization by decimal scaling if you want something to be easy to comprehend, easy to read. Because regardless of which k you end up with, it's easy to comprehend. It's just moving the dot to the left, basically. While you use min-max normalization, if you want to use the value range, you select 100%. Both min-max normalization and normalization by decimal scaling are very good if you have methods that run away with values that are above 1, for example. There are a lot of methods that exponentially multiply values that are bigger than 1. That's often also true for neural networks, by the way. And where min-max normalization and normalization by decimal scaling are very good. In most cases, you will use min-max normalization because easy reading of the values isn't that important. But since showing your results might also be sometimes more important than 100% easy calculations or 100% precise calculations, sometimes you are using normalization by decimal scaling as well. I guess everybody who was in exercises already did use these methods, so I won't get into more detail right now. But are there any questions on these methods? No. Just a little side note, because I like to put these notes into the lecture. Most often I will ask you one of these questions or one of these normalization methods in the exam, because you can pretty easily provide a list of values, a small list of values where you can calculate these normalization techniques. Of course, with easy values. Okay, then the last thing to talk about is discretization. Discretization is pretty important for a specific type of attribute. We already talked about nominal, ordinal, and numerical attributes in the data lecture. We need discretization, especially if we have not a given set of attribute values, but we have an infinite set of attribute values. And we want to end up with a discretized set of values. So not an infinite set anymore, but a definite set of values. This is often good if you want to reduce, for example, noise. Because noise is something that happens with very small value differences. And if you discretize any attribute, then you end up with a reduced noise, at least. It might also include errors, but noise can be reduced. If you are doing that, you put a continuous attribute into different buckets, more or less. And each of these buckets gets a label, an interval label, which is replacing the actual data value. It can reduce the data size of the original data set. It can also reduce noise, as I said. There are several methods that are either supervised or unsupervised. We will take a look at them. We will also take a look at splitting and merging different hierarchical approaches to this thing. And we can do that very recursively on any attribute. Let's start with typical methods. One method is binning. Binning is pretty much the same, or not the same, but related to histogram analysis. So we will end up with some of the same phrases I talked about last week during the histogram analysis part. Histogram analysis is therefore also a typical method for data discretization. Then we also have a third unsupervised approach, clustering. Clustering is something we will get into detail in the clustering lecture, but we will again have a small peek into that. Decision tree analysis is a supervised approach. Decision tree analysis is part of the classification lecture. So we will also take a look at that in detail later in the semester. However, today we will have a quick look at that. And then we have a correlation analysis, which is unsupervised, and you already know about chi-squared, so we can already talk about that in some detail. However, we will not get into 100% detail right now. Let's start with binning. Binning is, together with histogram analysis, the most basic approach for discretization. I already talked about histogram analysis with equal width and equal depth partitioning last week, where we had the two cases where we either put values of a certain range, certain fixed range, into the same bucket. So if we have a value range between 0 to 100, and we want to end up with 4 buckets, then we simply put everything between 0 and 24 into one bucket, 25 to 49 into one bucket, everything between 50 and 74 into one bucket, and everything between 75 to 100 into one bucket. It's not exactly the same range, but let's use 99. Into one bucket. That's equal with partitioning, because we are simply looking at the size, the range of intervals. And it should be equal width for each bucket. And then we can have equal depth partitioning, where we are free to use any range for any bucket, but we want to end up with roughly the same amount of values in each bucket. Both cases are used pretty much, used very often for discretization. Why would you want to use equal depth partitioning for discretization? Any ideas? Last week in histogram analysis, I told you that equal depth partitioning is not that often used. Now I tell you in discretization, we are using equal depth more often, roughly equal to equal width. Well, the answer is already on the slides. We have a pretty much good data scaling in here. So we, have more precise buckets for buckets where many values are clustered, because then the value range will get pretty small at these buckets. And at buckets where less values are, for example, in outlier regions, we have bigger buckets. So if we are talking about a numerical sense, then we would use, for example, the mean as the label, category label for every bucket. Then the outlier buckets will get less precise, while the cluster buckets are more precise. So let's do an example for that. Let's use the value range of 0 to 99 again, and we are using 4 buckets again. And let's say we have 0, 1, 2, 3, and 4 and 5, and then we have 75 and 99. So we have 8 values in total. Since we are using equal def, we are putting 2 values, 2 values, 2 values, and 2 values into one bucket, even if they have different value ranges. For this bucket, we end up with a mean of 0.5. So let's use 0.5 as a representing label of both 0 and 1. We do the same for 2 and 3, where we end up with a label of 2.5. And 4 and 5, we end up with a label of 3.5. Sorry? 4.5, yeah. You're right. And then here, let's use 100, it's easier to calculate, I think. 87.5, I think. So it's pretty precise. The label is pretty precise for the values where we have a lot of values being clustered. We have a less precise label for the outliers in here. And that's something we wouldn't have if we would have used equal width partitioning, because then all of the first 6 values would have ended up with 12.5 as a label, while these would have been ended up with 87.5 as well. So equal depth partitioning is sometimes, at least in discretization, something we want to use, because it gets more precise the more values are in a region. Now, since we've talked about binning, so we talked about equal depth and equal width partitioning, we can also talk about data smoothing. So which value represents values of the buckets? I've already done that in here. This would be the smoothing part, selecting a label for the values. And that's either done, and it's most often done, by bin means. So we calculate the bin mean, just as we have done on the right here. And we simply put every value, regardless of the original value, onto this bin mean value. So in the bin 1 in here, we have 4, 8, 9, and 15 as original values, and we put everything to the bin mean of 9 after the bin data smoothing. Same for bin 2, where we put everything to a bin mean of 23, and same for bin 3, where we put everything to a bin mean of 29. And same we have done here with 0.5, 2.5, 4.5, 87.5. We can also apply smoothing by bin boundaries, where we take a look at the lowest, at the minimum value of every bin and the maximum value of every bin, and we simply select the closest value to the original value to represent the entity. Note that by smoothing by bin means, we only had one value for every value in the bin, but in smoothing by bin boundaries, we can have two different values in the same bin. Since 4, 8, and 9 are all closer to 4 than to 15, these end up at 4. 15 is, of course, closer to 15, so it ends up at 15. Smoothing by bin boundaries is therefore a little bit more complex. We end up with 6 values for 3 bins. And that's true in any case where we have different values within each bin. The only case where we do not end up with 2 values for each bin is where the bin only contains 1 difference value. Because then the minimum and the maximum bin boundary would be the same, and therefore the bin boundaries would be the same. Yeah. This is, I hope easy to understand how it's done, and it's easy to be done in reality. We do that in the exercise. Again, I think you already have done that for an example, or for example, temperature values, and it's pretty often done for smoothing data, discretization of data. I would say most often you would use bin means, but sometimes you would also use bin boundaries to better display differences within the bin. Histogram analysis is just the visual variant of that. So you could do the same, but visually, and then you are at the same place. The next unsupervised method we have to talk about is classification and also correlation analysis. Classification analysis is, for example, done by a decision tree analysis, where you try to put your values into certain classes. Classification is supervised since you have to have these class labels at hand. So you have to know which classes can result out of the classification. For example, you can classify different vehicles into cars, into transporters, into boats, into airplanes, and you already know about these categories, and you simply put new entities into these categories. For example, by using a decision tree. So a decision tree might be, one node in a decision tree might be, can it fly? Yes or no. When you end either at the airplane side, flying vehicle side, or at the ground vehicle side. We will talk about decision tree analysis in the chapter of classification, and I think it gets pretty obvious then. We will cover the details in chapter 6, but you can, of course, use this to discretize entities as well, because if you have a certain specific vehicle and you put it into a class and then use the class as the representation of that entity, then it's pretty easy, because you might have 100 different attributes describing the original entity, and now you end up at it's a car. It's, of course, more discrete than the original infinite values it can have. Yeah, that's enough, I guess, for now. We will talk about that in chapter 6 again. Then we have correlation analysis, where we can, for example, apply methods like chi-squared merge or a chi-squared based discretization, where we also try to find class information and try to merge fitting classes together. We end up at a hierarchical scale until we end up at a certain stopping condition. We will not talk about chi-squared merge in detail right now. We will have a certain excursus in classification on that as well. But basically, the more entities correlate with each other, the closer, the more similar they are to each other, and therefore end up in similar classes, and therefore we can build up a hierarchy out of these similar things. A concept hierarchy or a hierarchy in general is also something you might want to use for discretization. One good example for that are locations. You already know about locations. If I'm talking about where to meet, you can either say we are meeting in Erlangen. Well, that's a rough meeting point. However, it's not precise enough to really meet with each other. If I say we are meeting in Erlangen in the Kauerstraße, then it's a little bit more detailed. And the probability that we are meeting is higher. But still, it's not 100% given. The next level would be to say we are meeting in Erlangen in the Kauerstraße in house number 14. Now it gets even more precise. The next thing would be the room number of this building, and so on. So that's a concept hierarchy. And we can organize a lot of concepts hierarchically. It's also something we will do in the next chapter of data warehousing a lot, because a lot of different concepts can be put in these different hierarchies. And it can be used to aggregate or discretize data. To do that, we can either start bottom up, so we can start at low-level concepts, so the precise address, and we try to find higher-level concepts to fit that. We can do that also the other way around, so top-down, not bottom-up. Concept hierarchy generation for nominal data requires you a little to have a little bit of knowledge about the certain case. But we already talked about a location hierarchy set. You can, of course, even start higher at the country, then the state, then the city, then the streets, then the house number, then the room number, and so on. That's a typical hierarchy set. If you go to a higher level, then you discretize the data of a lower level, more or less. You can try to generate hierarchies automatically if you take a look at the analysis of number of distinct values. So typically it's given that a lower level of granularity always has more values than a higher level of granularity. You will have more streets in our world than you have cities in our world. You will have more cities in our world than you have countries in our world, and so on. The higher you go, the lower the number of different entities gets. So if you are in doubt, which is the lower granularity, which is the higher granularity, can always go by the number of different entities in each level. But of course, you have to have the information that these are linked levels of granularity. We have more streets than cities, more cities than states, more states than countries. Yeah, that's pretty obvious. Yeah, but you have to have the information that these are linked together in a hierarchy to even apply that. Okay. Of course, these hierarchies can then be used to discreticize data. I already said that. So yeah, that's the link to our chapter. We will talk about concept hierarchies in a second again, once we get to data warehousing. But for now, a little summary of a chapter of preprocessing. We talked about data quality 2 weeks ago, where we talked about accuracy, completeness, consistency, timeliness, believability, interpretability, and things like that. We also talked about different dirty data in our data set and how to handle that in a high level. You have taken a closer look at that in the exercises and learned about how to fix dirty data. Then we talked about a big problem in data mining, where we have to integrate different data sets. And we might end up, for example, with M and F and male and female in different data sources. And we have to integrate that together. We talked about data reduction, for example, by dimensionality reduction, so PCA, for example, or the wavelet transform. And we talked about numerosity reduction a little bit, but much quicker than the dimensionality reduction. Sampling would be a good example for that. Data compression is something that happens as well, but we didn't talk about that in detail, we just mentioned it. And then lastly, we talked about data transformation and data discretization with normalization, very important, and also discretization by different methods, for example, binning, but also concept hierarchy generation. Are there any questions regarding the chapter of preprocessing? Okay, doesn't seem like it, so we can go to the next chapter, which is data warehousing and online analytical processing. No. Data warehousing and online analytical processing. Online analytical processing can be shortened as OLAP. I will call it OLAP in the German pronunciation most often, just because I can't remember to call it the English way most often, but yeah, I'm talking about online analytical processing in most cases. In data warehousing, we will talk about first, what's a data warehouse? So what are the basic concepts of a data warehouse? Why are we even talking about data warehouses? We are in KDD. Why are we talking about data warehouses? Then we talk about data house modeling, and therefore also data cubes and OLAP. So online analytical processing. That's where we will get back to the concept hierarchies, because these are integral thing within data cubes. We will also talk about data warehouse design and usage, and we will give a summary on how to use data warehousing and data mining together. And then, of course, we summarize the whole chapter. Let's start with the basic concepts of a data warehouse first. What's a data warehouse? Well, there is a very important person in this domain. William H. Inman is so-called the father of data warehousing, and he defined data warehousing as a data warehouse is a subject-oriented, integrated, time-variant, and non-volatile collection of data in support of data management decision-making process. This is the most often used definition of a data warehouse. We will get into what these four terms are talking about in a second. It's pretty easy to understand, but of course there are other definitions. For example, you can talk about a data warehousing as a system that extracts, cleans, conforms, and delivers source data into a dimensional data store as well. You can also talk about data warehouses as a decision-making database. Or a database that includes consolidated historical data for analysis. The important thing is that all of these agree that data warehouses are about historical data that are used to do data mining. That's the common idea of these definitions. Data warehousing is the process of constructing and using data warehouses. So basically, if you want to prepare data for data mining in a data warehouse, you are doing data warehousing. If you are using a data warehouse for data mining, then you are also in the process of data warehousing. Back to the definition of Inman. He called a data warehouse subject-oriented. Subject-oriented means that we are trying to build our data warehouse around a certain object or subject. For example, we can build a customer data warehouse where we have all information about the customers. We can build a product data warehouse where we have all the information around our products. We can build a sales department data warehouse where we have all the information about sales. Basically, a data warehouse wouldn't include all the information of the world consolidated into one data warehouse. That wouldn't be subject-oriented anymore. Well, you can say subject would be the world, but that's too broad. We try to have a very major subject, which is the focus of our data analysis we want to perform on the data warehouse. So we try to collect data that is linked to a certain subject on which we want to perform data analysis, data mining. It's very important that a data warehouse is never about daily operations. So a data warehouse is not talking about, is not the place where you put your currently occurring transaction in that and try to find and try to run your actual warehouse around that. It's more about to provide a simple and concise view around a particular subject issue. A data warehouse is also integrated. It's most often, it's not 100% given, but most often it's constructed by integrating multiple data sources. So we can, for example, include different databases, transactional databases. So everyday databases into a data warehouse. We can also have Excel files we are using for the data warehouse. We can have PDFs that we are including information out of into our data warehouse. It doesn't have to be always relational databases. It can be heterogeneous sources. To put data into a data warehouse, we are already performing some pre-processing steps. We are performing, for example, data cleaning steps, and we are performing data integration steps, which are pretty much linked to each other, which you should already know. But that's the reason why we are talking about data warehouses after the pre-processing lecture, because you already know about data cleaning, you already know about data integration, and these steps should be done before putting data or while putting data into a data warehouse. There is a pretty important process which is abbreviated as ETL, extract, transform, load, which is done to put data into a data warehouse. We will get into that in a second, but remember ETL because it becomes pretty important. A data warehouse is time variant. That means that we are storing data a lot longer than in an operational database. An operational database is about current data, data that is currently relevant. For example, new orders which have to be processed and get in. In many cases, these operational databases hold data for 1 year, maybe 2 years, but then they get deleted. In a data warehouse, we have a significantly longer time horizon. So we put data into the data warehouse on a historical perspective. 10, 15, 20 years. It will get longer the longer we have data mining. I'm pretty much sure data warehouses are here to store data which is currently relevant for as long as a company exists. We are storing data very, very long because we want to perform analysis around multiple years. It's very important that we often or most often have key structured that are containing any element of time, either explicit or implicitly. So we are always storing when this entity was put into the database or was relevant. We will see that afterwards as well. And then it's a non-volatile store of data. So it's not just a link to the original database, but a separate copy of the data from the original operational database. Because in databases, in operational databases, you will most often change records. You will, for example, change the status of an order to fulfilled after you fulfilled the order. In a data warehouse, you do not have any operational updates of data sets. You just put in data, read only, append only. Put data in, the data warehouse gets bigger, bigger, and bigger, but changes are not that often done. There are certain exceptions to that, but we will not get into those. Most often it's just append only. So you initially load data, you update by appending the data, and then you just access the data to perform data mining operations on the data. Basically, I've already talked about how to use the data warehouse. The most important part for us is data mining. But there are three kinds of data warehouse applications. We either have information processing, where we do very basic statistical analysis on the data. For example, how many males and females are in our customers. During the first lecture, we talked about these simple analysis not being data mining, because they are too simple. However, they can be done on a data warehouse. Then we can have analytical processing, where we use the multi-dimensional organization of a data warehouse, where we will get to in the data cube section, to perform very basic OLAP operations, such as slicing, dicing, drilling, and pivoting. Also, pretty easy operations. You do not know about them yet. You will get to know them in a second. Pretty basic. And then, and that's the most important part, we have data mining, where we try to find hidden patterns within the data sets at hand to, for example, improve our business or to improve our customer relations. So we can perform every data mining method on a data warehouse, and we have the big advantage that it's already pre-processed to a certain degree. So we can skip, for example, data integration. We can skip data cleaning to a certain degree. And that's something that is pretty important, because we can do that one time on our data set, once it becomes historical, and then use it for a lot of different data mining operations. And we do not have to perform the data cleaning and data integration every time we are putting in data. So data warehouses are often the base where, which is used to data mine. Let's compare two different operations. We already talked about daily databases, operational databases, I've seen you. And we already talked about OLAP databases, data warehouses. First the question. Okay, I think the question was whether if we already have put data into a data warehouse, which is a copy of original data set, once we are using that for data mining, do we again do a copy on that data, or do we use just the data warehouse? Is this your question? Override. Okay, if you are doing more pre-processing on the data, whether you override the data on the data warehouse? No. The data warehouse is a thing you shouldn't be. Where's my pointer? We talked about non-volatile data in data warehouses. So once you put data into a data warehouse, after integrating the data as good as it is into a data warehouse, you shouldn't change it anymore. And therefore, if you perform additional pre-processing steps in your data mining project, you wouldn't push these changes back into the data warehouse, because that would be against the non-volatile theme of a data warehouse. Basically, you would try to put data into the data warehouse which is pre-processed to a level that supports every data mining project in there. And the additional pre-processing steps you're doing in the specific data mining project are tailored to this specific data mining project, but not to every other data mining project. And therefore, it wouldn't make any sense to push these changes back into the data warehouse, since there should only be general pre-processing steps. A data warehouse always contains preprocessed data because you want to clean the data, to integrate the data. It's integrated nonetheless, so you have multiple sources. You have to integrate these data sets. And the data warehouse is about not raw data, but integrated data and preprocessed data, cleaned data. Yeah. But to a degree where it supports every data mining project, which is possible in this data, around a certain subject again. So if you're subject-oriented, you shouldn't have to you of course focus your preprocessing on the subject as well. Yeah. Okay, back to OLTP, which is online analytical, online transactional processing. OLTP is the basic day-to-day use transactional database. So the database where you put your day-to-day operation into. An OLTP database is very application-oriented. It's very current, up-to-date. It's most often flat relational. It's isolated, and it's very repetitive in usage. Basically, in an OLTP database, you expect reads and writes. You change a lot of data, you read a lot of data. In very short and simple transactions. So basically, give me transaction Y, I will change the status of transaction Y from processing to fulfilled. That would be an operation in an OLTP database. We most often access only very little records per SQL query, and we have a lot of different users on the database. Because we have all the websites, for example, going onto that database. A database in this dimension is most often very comparatively small. I've written 100 MB to GB. There are bigger transactional databases. I will give you that. There are databases, OLTP databases also in the terabytes and even petabytes dimensions. But these are smaller than the OLAP databases. It tries to process transactions. So single transactions can be updated. It's day-to-day use. Compared to that, we have OLAP databases, which are about online analytical processing. So it's about data mining, where we try to support our decision support, our data mining operations. Where we do not have current data, but we have historical data. We most often have summarized data. We have integrated data, consolidated data, and multidimensional data, which is something we will get to. In OLAP databases, we do not have reads and writes a lot. We have a lot of scans, and we simply append new data into the database once, so we can access it for our scans. But most an OLAP database will do is reading the database and a lot of records at the same time to perform data mining operations. Most often, these are very complex queries, since we are accessing different levels of a data cube at the same time. Complex in a multidimensional way. We do not have that many users because it's not about day-to-day operations, but of supporting our knowledge worker. So basically you. And since it's historical data, these tend to be a lot bigger than the OLTP databases, since it stores the data of a lot of OLTP databases in one OLAP database. here we do not try to find a good way to process a lot of transactions in parallel, but we try to process bigger queries at the same time. So here we have a lot of smaller transactions. In OLAP we have a lot less transactions, but bigger transactions. Yeah, which leads us to the question, why do we have OLTP and OLAP? Why do we have two different databases? Well, in a database management system, DBMS, we are tuning the whole system for OLTP. There are a lot of researchers, a lot of people, IT experts, that are trying to optimize database management systems to be as fast as possible in handling multiple millions of transactions at the same time. We do have chairs, IT chairs, working on database management systems for the past 30, 40 years. And we are still optimizing database management systems for OLTP to this day. Because it's that important. These database management systems also get bigger and bigger, and therefore have to be tuned as well. A big problem we have seen in this optimization is once we optimize for a lot of transactions being handled at the same time, we lose other capabilities. It's a trade-off. So if we want to support very big queries optimized for OLAP, then we have to perform other optimizations. And therefore, we do not only have relational database management systems, but we also have data warehouses, which are tuned for these big operations. Less, but bigger operations. Also, if you would perform a big query on an operational day-to-day operation database management system, of course, you would hurt the performance of this database management system. Since it takes a lot of CPU cycles, it takes a lot of memory, it takes a lot of, also I/O. So we have different focus on both systems. And we optimize the systems for different use cases. So in a database management system, we, for example, remove data which isn't current anymore, which isn't needed anymore from the data store. It's missing this data sets, but in a data warehouse, we store all data, all historical data, so we can perform historical analysis. In a data warehouse, we try to aggregate, summarize data from heterogeneous sources, which is something we do not do in a database management system, where we only have one source. And in a data warehouse, we also try to have a better data quality than in a day-to-day database. A big side note is that while I'm saying you shouldn't do database management or day-to-day operations and analysis on the same system, these days there are some or even a lot of systems which are exactly trying to do that. So putting the optimizations into the same system. There is a lot of research on that, and there's a specific name to do that. However, it's still a little bit clunky to do that. Since we have to have different optimizations, we can, of course, put different optimizations into the same piece of software and then simply switch between the two optimizations depending on the use case. However, it's not that nice to do that if you have enough power in your computer in your database management system to handle both at the same time, well, you can do that. Yeah, it doesn't mean you should do that. However, there are 3 different data warehouse models. At one place, we have the enterprise warehouse. This enterprise warehouse connects all the information around the subject of the entire organization. So the subject of an enterprise warehouse is the entire organization. It stores every data point in our organization. Then you can apply a data mart on a subset of this enterprise warehouse, which provides the data which should be accessible to certain domains. For example, you can have a data mart for your business analysts. They might not be allowed to access certain employee data sets. Therefore, they only get a subset of the enterprise warehouse for analysis. This is called a data warehouse. Very often, data marts contain highly summarized data, while the enterprise warehouse contains more fine granular data. You can have independent and dependent data marts. An independent data mart would, again, not rely on an enterprise warehouse, but would be, for example, a copy or a thing like that. While a dependent data mart is just a view on the data warehouse, on the enterprise warehouse. And then there is a virtual warehouse, which is basically what I've pointed out here in the note. You can also have a data warehouse which is just a few over operational databases. So it's just a virtualization of the data on the database management system. Yeah. These views are sometimes not materialized, therefore are not even copies, and therefore performance gets a lot worse with these virtual warehouses. I wouldn't recommend to do that yet if you are not having a powerful enough database management system. And a big problem with virtual warehouse is also you can't integrate data, can't clean data. You have to have a very clean relational database to work on. If the data is dirty, it most often can't be cleaned with a virtual warehouse. You can, and SQL is Turing complete, you can provide some cleaning within the SQL query, for example. However, that's not that good to do. Yeah. We already talked about ETL, extract, transform, and load. This is a 3-step, or even, okay, your question? Your question was whether virtual warehouses are a subset of what? Of a warehouse. No, it's a specific form of a warehouse. While an enterprise warehouse would be a copy of original data, an integrated, clean copy of the data, a virtual warehouse isn't a copy. It's just a view. A view is a SQL construct, a SQL term, where you, let's do it this way. You know about SQL queries, hopefully. So you can, for example, say, select X from table Y. Yeah, that's a SQL query, a very basic SQL query. Maybe let's do a little where in here as well, where we say X point value equals 9, whatever, okay? A view in SQL sense, in a database sense, would be to store the result of that SQL query into a so-called view. So the view A, in this case, would simply run this query, and the resulting relation of that query would be called A. And a virtual warehouse is more or less consistent out of multiple of these queries, which are more complex than this query, of course. This is a pretty simple query. Most often you have some mergers of different tables, and you merge together certain tables to build a bigger table, which is then so-called the virtual warehouse, because it's just a materialized or non-materialized set of SQL queries. So while an enterprise warehouse would really load the data and store it in a separate database, a virtual warehouse is just consistent out of different SQL queries on the operational database. It's a different thing to do. You still look a little bit confused. It's okay? Okay. So it's a different thing to do. A virtual warehouse is really using views, and maybe you do not know about materialized and non-materialized views. There are different concepts where this view either is run every time you ask for A, that is non-materialized, and if it's cached in between, then it's materialized. You did have a question as well? Yeah, you can say that with a real data warehouse, you would copy the data and alter the data by doing the ETL process. That's the thing that is coming up right now. You alter the data, to transform the data to fit into your data warehouse. In a virtual warehouse, you would not alter it that much. You would still alter that because you would, for example, perform selections. You would perform some transformations as well within the SQL query on this thing. So I already told you this is a pretty simple query, since I simply come up with that query right now. A real SQL query to build a data warehouse would be far more complex. It would span hundreds of lines and would perform certainly a lot of actions to put in some transformations, but these transformations are not permanent, since it's just a virtualization of this thing. And in a virtual warehouse, you are not able, or most often not able, to clean the data as good as you are with a data warehouse. But some things, like, for example, transforming male and female to M and F is something you can do with a query as well, obviously. And you would do, because integration is still important with virtual warehouses. Okay, now to the extract, transform, load process. Basically, the extract, transform, load process has three major steps: extract, transform, and load. However, depending on the source, where you, on the literature you're looking up for ETL, you will end up with 5, 7, even 20 different steps to perform in ETL. I think that this 5-step process is the most often used process. There you start with extracting data to try to find data in multiple heterogeneous and external sources. So databases, relational database management systems, but also Excel files, PDFs, and things like that. And you extract the data from these original sources to be ready to be put into a data warehouse. In the next step, you try to clean the data. That means that you try to detect errors in the data and try to fix them as good as possible. We already know that not every error in the data can be detected and can be fixed, but you try it as good as possible. And the cleaner you get the data, the better your data warehouse gets in the end. After that, you try to transform the data. Cleaning and transformation are pretty much, intertwined with each other. You can say cleaning is just a subset of transformation. That's why cleaning isn't in the original 3 steps. Transforming the data in this 5 process step does mean that you try to put them into a certain new format. For example, in the multi-dimensional scheme we are coming up with in a second. Or trying to put male and females to the same naming scheme, putting grades into the same system. That's transformation. Then you are loading the data. And loading the data is different from extracting the data. Extracting the data is really about loading the data from the original data source. Loading the data is talking about loading the data into the new database, the summarized, pre-processed data into the database. So extracting from original sources, loading into the new data warehouse. And by loading, you are sorting, you are summarizing if wanted, you are checking integrity in the data set, you're building indexes and partitions and things like that. So you're putting the clean data, the transformed data, into the new data warehouse. And now you have data in the data warehouse. Of course, you have to refresh data, so to append new updates from the original data sources. Append. Update, very important, doesn't include changing. Most often, it's more about appending data to the data set. Yeah. Sorting, summarizing, consolidating as part of a transformation, most often you wouldn't do that. You wouldn't count sorting and summarizing as part of the transformation step, because these are operations you can do in the multidimensional scheme we are shortly talking about. And these multidimensional schemes are part of the data warehouse itself, and therefore not about a general pre-processing step. And that's why these are most often counted towards the loading step rather than the transformation step. Of course, they are some kind of transformation. You're right with that. And if it's a summarization you would perform, nonetheless, you can argue to do that as part of a transformation step, but it's most often done to fit the data warehouse, not as a general pre-processing step. And that's the difference. That doing things you do just to fit the data warehouse, the specific data warehouse at hand, those are part of a loading step, and general pre-processing steps you would do regardless of the design of the data warehouse, those are part of a transformation step. Yeah. Okay. So extract, transform, load. The most important steps are extract, transform, and load, but other things are contained as well. Yeah. Okay, the question was, if we append data in the refreshing step, what happens to the non-updated data in the data warehouse? Well, most often you let's say you have a data source like a transactional data warehouse system where you store orders, okay? Then you first create your data warehouse, you put in all the data, all the orders up to December 2025. You put these into the data warehouse, you extract the data from original database system, you transform the data to fit your pre-processing scheme, you load the data into the data warehouse, and now we are in May 2026. A lot of more orders came in the original database system, and we have to refresh our data. Then you would simply take a look at the new orders from January 2026 up to May 2026 and put these through the process of extracting, transforming, and loading, and append them to the database management system. If there are changes to previously made orders, you most often would disregard them in the data warehouse to a certain point. There are exceptions to it. For example, if you have an order that is getting deleted, then you can, for example, in the data warehouse, have a separate table where you put in deletions for the data set. That depends a lot on the data warehouse at hand. Then it might happen that one of your customers married and took the name of the spouse. Then, of course, you should also put this change in your data warehouse in some kind. Most often, append only, you would put a change notification in a separate column to not alter existing data warehouse content. It depends a lot on the system you have at hand. Sometimes you would also update, but that's less often done to really update data sets. Is your question answered? Okay. Yeah. Yeah, that's the reason. So the question was that this changing of data sets would mess with the non-volatile status of data warehouses, which is part of the imminent definition of data warehouses. That's the reason why we have an append-only strategy in most cases, because appending is not altering existing data most often. That's why we have most often more of a change log being appended than really changing existing data. As I said, there are exceptions to that. Sometimes you would really update data sets, but that's against the non-volatile definition of a data warehouse, so you try to avoid that. But we have to be honest, in universities we teach something theoretically, and the most optimized theoretical way of doing things, and in the real world you would often disregard what you learned at the university and do it some other way, just as you like, even if it's not optimal in a theoretical sense. And therefore, I have to admit, there are data warehouses where things are getting updated. That's happening. I can't lie to you in that sense. That's something that shouldn't happen due to certain other reasons, but it happens. Also, it's against the strict theoretical definition of a data warehouse. I want to at least get to 2 more slides. So I will speed up right now because we only have 5 minutes left. Before we get to the next chapter, we first have to also talk about metadata repositories. Metadata is something that is pretty important. It's getting pretty important the more data you have at hand. Metadata is data about data. For example, having the mean of a table of an attribute is data about this attribute, data about data. So a mean is a metadata point about an attribute, for example. In data warehouses, we have 3 different kinds of metadata. There are business, process, and technical metadata sets. Business metadata is about business terms and definitions. For example, a business metadata point can be data ownership. So which company entity, for example, owns the data point that is put into the database. Different data ownership often happens due to different data sources being integrated into a data warehouse. If you have a sales database and the employee database being integrated into one data warehouse, of course, different owners have different rights, permissions on the data sets. Because a sales manager isn't allowed to have data about employee Y. They shouldn't be able to see how much money they earn, for example. Or in a university sense, different roles in the university have different ownerships and therefore see different things. I, for example, can see only grades that are linked to our chair. I can see your grades at our chair. I can see which grades you got at other chairs, because we own the data of the grades of our chair. We don't own the grades of a chair of Informatics 5, for example. So I can't look that up. These ownerships are important. It's also important to know who owns data if there are problems with these data sets. So if there's a problem with a data point, who should I contact to fix that problem? Then we have process execution metadata. So for example, how often do we refresh the data out of database system Y? That's a process execution metadata point. How do we aggregate these data points? How many rows did we reject or successfully inject in our data warehouse? These are process execution metadata points, for example. And then we have technical metadata. So which tables do we have? Which attributes do we have in these tables? What are the results of data profiling? So min, max, median, mean, things like that. And what's the data lineage? So what changed in the data if we are changing data, for example? These metadata points are all stored within a data warehouse, although they are not the original data being extracted. But they become relevant for certain actions. For example, having the data ownership is good if we have problems with one data point, as I said. It's also important to know about data ownership. For example, if we are taking a look at different source systems, ERP, CRM, for example, putting these via the ETL pipeline into a data warehouse. Data ownerships are often dependent on different data sources, but they can also lead to different data marts, so different views on the data, because different ownerships might allow different people different views on the data. And therefore, we might have a data mart for our HR department. We might have a data mart for our sales department. We might have a data mart for our IT department. And depending on the ownership, different people might need different data marts because they have different rights on the data or they have different subjects interests in the data. and then the data marts are used to provide different analysis on the data. Okay, I'm already 1 minute over time. Nevertheless, the question, are there any more questions? Okay. If there aren't any more questions, then we will continue in this chapter next week with data cubes and OLAP. Yeah, see you next week on Wednesday at the same time, at the same place. Have a nice time.